All right, let's go back to the on your owns. Mr. Parker is going to be using the computer for a bit. He gets to listen in on how well behaved you all are. And let's go back to the on your owns we started before. To be honest with you, I don't remember where we left off, but let's pick up with the on your owns. Third edition, 5.4 through 5.8 is where we were at, and these were drawing the Vesper three-dimensional geometries. And then we can actually just transition into, because I don't have a lot more for you on polar, nonpolar molecules, the principle I've just used up there with the water molecule applies, and we can work through some examples and problems of those as well. So let's go ahead and do that. We're going to use the third edition, 5.4 through 5.8, and then second edition, folks, if you'll look at your second edition, and if there are others in there that are different from the ones we presented, you want to go over them, let me know, and we'll do those as well. Third edition is 185. Second edition is, somebody help me, 270, 280, in that ballpark? It's in Module 9. It's going to be 9.4 through 9.8 on your own, probably. Okay. Stinks to be you, huh? Stinks to be you. All right, which one are we on? You help me out because we did a couple of them in class.
We're on what are the shape and bond angle of the SICO 201.
Were we all the way at the end on 5.8?
I think we were. I mean, yeah,
Okay.
Yeah, we're on.
Middle of the SICL 20. All right. Class is back in. Let's go. Right. The SICL20 molecule. What is the shape and bond angle of that molecule? So what's our first step we're going to do in assessing? We need to have, first of all, before we can do the three-dimensional, we need to have a good two-dimensional diagram. We need to start with a good Lewis structure before we can go to the Vesper model. So, SICL20. What do I normally do? What's my first step? The way I've been trying to get you to do it. We're going to identify that one. In order to make sure we get it right, I go ahead and draw each element and draw their individual Lewis structures. So it's an Si, a Cl, and knowing that we're going to have two of them, and an oxygen. Now oxygen is a 4A element, so it has the 4 dots. Chlorine is a 7A, so we're going to end up with an oxygen is a 6. Okay? So the unbonded electron count also is the same number as the open addresses count. This silicon has 4, chlorine has 1, oxygen has 2. So noting that silicon has the highest number of unbonded electrons, also the other way of thinking of that is the most open addresses to bond with someone else. So it's going to be our center element. It's going to be our pivot element, all right? So I'm going to redraw this. And I know I'm going to need, in my element, or my molecule, excuse me, I've been told that I've got 1 oxygen and 2 chlorines. So I've got 4 locations. I'm just going to put the oxygen at one of them and put the chlorines at 2 of the others. Okay? And I'm going to orient my single unbonded electron in each of these Lewises towards the unbonded electron of my pivot atom, my central atom. So chlorine has 7. I'm going to put the single there. Has the single there. And the oxygen, one of my singles, I know I've got a pair, and another unbonded like that. Okay, so I've basically just oriented the individual Lewis structures and brought them close to each other. And I see that I have, first of all, I'm going to go through and make my bonds for the 2 that are in proximity to one another. And then I look at the counts. This chlorine sees how many electrons belonging to it? 8. So is it satisfied? Okay. This chlorine sees 8. It's satisfied. Oxygen sees 7, and silicon sees 7. So there's another share needed for both silicon and oxygen. Well, silicon does have another unbonded electron that it can donate, and oxygen can donate its unbonded electron to form a bonded pair. We know the chlorines are already satisfied, and we haven't messed with them at all. Now we look over to the oxygen, and it now sees 2, 4, 5, 6, 7, 8. And silicon sees 1, 2, 3, 4, 5, 6, 7, 8. So the octet rule for every one of the elements has been satisfied. Okay? With this structure, this is a two-dimensional Lewis structure. Now we need to draw this as a three-dimensional Vesper diagram. Now before we go anywhere, how many things, I know it's kind of nebulous, how many things are connected around the central pivot atom, the SI atom? For Vesper, all we're looking at is bonds, and double bonds are the same as single bonds. There's no differentiation. They're bonded. And electron pairs. So right here there are three things. There's a single bond, and a double bond. There's three things. When we have a central atom with three things, how are they going to orient themselves? Think of it as a hub with three spokes. And the idea is the three spokes want to get as far apart from one another as possible. Right? Do you see, can you visualize that it's still going to be in a plane? We're going to have a center. And think of it as a center and three bars. If I got three bars and they want to get as far apart from one another as possible, they're going to set themselves up in this kind of an orientation. And what is the angle going to be between each of the bonds or each of the bars? We've got 360 divided by 3. 120. So each of those angles is going to be 120 degrees. The angle between the bonds is going to be 120 degrees. Now, if any one of these were to come out of the plane of the board, let's say if this one came up, you can see how in a sense it would be getting farther away from some, but it would be getting closer to others, right? It would have a front-back force where it would be farther away, but in the back and closer in the front. And it doesn't want to be closer in any way. It's always seeking to be as far away as possible. And so with a central atom with three connections, each one of them is going to move as far away as they can, and it's going to result in a flat plane. Now remember, it's a three-dimensional object, but we can draw it in a flat plane because the bonds are all going to be in a plane with an angle between them of 120 degrees. Okay? All right. So if we take this idea and we go ahead and draw our molecule in that way, we have the center being our silicon. And let's go ahead and draw, for symmetry, I'm going to go ahead and put the up, because we're used to seeing it this way. I'll put my oxygen, and a chlorine, and a chlorine. Technically, I would go through then and put my other valence electrons around there. Now, but with the oxygen, to be technically correct, how would I orient my unbonded electron pairs around oxygen? See, if we just look at oxygen, what does oxygen have around it? It has three things around it, too, right? It has a double bond with silicon, which you've indicated here, and then it's got two electron pairs. And so technically what I would do is go here and put my unbonded pairs at a slant and kind of give you the idea that, hey, around oxygen, it has three things as well. They're not going to be here and here. They're going to be oriented. We're going to show the orientation in that way to communicate this idea that they're pushing apart from each other as much as possible as well. All right? And so that is our three-dimensional Vesper diagram of this two-dimensional Lewis structure for this molecule, with bond angles of 120 degrees. 120 degrees for all three of these, all the way around. And what is that shape known as? Trigonal, right, triangular. Or I think, what is the phrase they use here? It's a trigonal, is the way I learned it, or the way I say it, but triangular? In the chart it says trigonal. Trigonal. So it's trigonal. Trigonal. G-O-N-A. It's trigonal. It's not triagonal or triangular, it's a trigonal. And this is a trigonal. We've had two kinds of trigonals so far. We've had a, remember the pyramidal, the thing that looks like my tripod? The pyramidal? It's actually known as a trigonal pyramidal. You just know it as pyramidal. But it's a trigonal in the sense it's got three bases on it, right? A trigonal pyramidal. This is just a straight trigonal. It's a planar trigonal, you may say, okay, because it's all in one plane. But it sets up three equally spaced spokes, three equally spaced segments, at the end of which are the elements that are bonded to the central atom. All right. So that satisfies all of the on your owns from the third edition. Second edition, were there any in there that you'd like to see worked out? No? Yes, sir.
Can you do the sulfur dibromide? No.
Sulfur dibromide. So it looks like that. Sulfur dibromide. So we're talking about sulfur and bromine. Sulfur is a, just want to make sure, I hate to do it. It's a 4, or excuse me, it's a 6, and bromine's a 7. So 6 and 7. I have a little inside knowledge, so I'll set it up that way. But I see I'm showing 7 around bromine, 6 around sulfur. Sulfur's looking for 2, bromine's looking for 1, and we've got 2 bromines in the molecule. So I'm going to put the second one over here. Okay? So bromines each have 7, looking for 1. Sulfur has 6, looking for 2. You gain 1 for every bond you make. So they want to make 1 bond. Well, there's 1. They want to make 1 bond. There's 1. They want to make 2 bonds. We have them. So there it is. Sulfur dibromide, excuse me. So that's the 2-dimensional Lewis structure. Now, who is willing to do the 3-dimensional Vesper? Okay? What do I need to change from the 2-dimensional Lewis to the 3-dimensional Vesper? Okay. I could. Mm-hmm. It's it's banned. That's right. So we're going to draw the two, excuse me. We're going to draw 2 bonds. Since we know we've got 2 of them, we can show it in 3-dimensional space. And we're going to show it, if we can, the ones we have, we're going to show them in the plane of the board. Remember, when we do our 3-dimensional, these 2, the one at 12 o'clock and about 4:30, those 2 are the ones that are in the plane of the board. Sorry, I don't mean to mock. It's fun for me. I'm sorry. So I'm glad you're laughing too. It's in the plane of the board. And so we're going to go ahead and put the 2 bonds that we do know, or that we do have, the 2 bromines, in the plane of the board here. And then sulfur here has 2 unbonded pairs. So we're going to just put those here, remembering that they're not in the plane of the board. They're going to be rotated around in a slightly different location. Because we have a sulfur with 4 things connected to it. 2 of them are bonds, and 2 of them are unbonded pairs. And this molecule is known as a bent molecule. I won't say that again for the tape. But a bent molecule. Okay, I'll translate it for you. Okay, just let me, indulge me. Bent molecule. 105. And what's its angle? 105 degrees. Great. It's 105 degrees. Now that's a bent molecule based upon a tetrahedral. You see that this is based on a tetrahedral. How do I know it's based on a tetrahedral? Because it has 4 things connected to the central atom. So if we understand the tetrahedral, that's why when I taught it, I started with 4, the tetrahedral. You take one off, now you've got the pyramidal. You take another one off, and now you have the bent. Okay? And the numbers are 109, 107, 105. So tetrahedral, 109, lose 1, 107, lose 2, 105. Then after that, you get into those that are based on 3, which we just did, a trigonal. And then you get those based on 2, which is linear. All right. So any questions now? We've done all the on your owns on molecular geometries. And, you know, frankly, the chart on page 182 and 183, I actually have a way that I look at that. I mean, if you memorize the chart, that's fine. What I'll probably do is do a supplemental video. I don't have time in here, but I'll make this video that kind of walks through what I just did with you all. It's based on a or a tetrahedral if it has 4. It's based upon a trigonal if it has 3. It's based upon, you know, and walk through each one of them. So if it has, like in this example, if it has 4 things and 2 of them are bonds and 2 of them are unbonded pairs, it's bent. If it has 4 things and 3 of them and 1 of them, or 3 of them are bonds and 1 of them is an unbonded pair, then it's a pyramidal. If it's 4 of them and they're all bonds, it's a tetrahedral.